Yep. All right, here we go. We're going to do volumes of solids with known cross sections today. This is not on this year's AP exam uh, because of what's going down, but felt like I should teach it to you since we were so close to finishing that volume section. It's a pretty neat topic. So let's get after it. All right, so here we go. So it says, let's use the area enclosed between the graphs of y equals 4 minus x squared and y equals x squared to be the base of a solid. All right, so now this is a little different because we're going to create volumes now, not by revolution, but volumes where we look in the xy plane, an area between two curves, for example, and we make that the base or the bottom of our solid. And then we're going to pick cross sections that are perpendicular to that base, and they're going to be all different shapes. So we're actually going to start off with the cross sections being squares. All right, so let's just do a couple things here. First. So first things first, let's get our TI calculators out and let's just graph this region, right? So in y equals, you're going to put y1, it's going to be 4 minus x squared, and y2, you're going to be x squared. If we graph it, this is what we get. So again, just for that, so we're understanding this, what we're doing here, all right, is we're saying this region here is going to be what we're going to use as the base of our solid. So that's kind of like the bottom of the solid. It's going to be a flat bottom, and it's going to have that shape. And now what I want is I want to create a solid where the cross sections perpendicular to that base are going to be, we'll just start off with squares, say. So we're going to draw squares. And you're like, well, what the heck does that mean? So let's go over to our nice friendly little GeoGebra app here. All right. So if we look at our GeoGebra app, which for some reason just blanked out on me, let's refresh that page. All right, so we get this. Now, these are the wrong functions by default. So it turns out that I can put in the right function. So I'm going to take a couple seconds and do that. 4 minus x squared for that guy. I'm going to do x squared for this guy. And then these I can figure out in a second, but I'm just going to go ahead and put them in because I know what they are. Like, what are you putting in? We'll explain that in 1 second. Okay. And, oop. 414. That should be good. Right. So there it is. Perfect. All right. So that's just kind of cutting off that section of the two curves. So you like that looks really weird. There's 3 axes. So you got your y-axis, your x-axis, and now your z-axis. And the idea here is, let me zoom in a little bit. The idea is that we're now going to create or make cross sections that are perpendicular to that base. So that's one cross section. So think of that as like a square little tile. You can also put in 3 cross sections, right? And this is a little weird feature, but I'll do it. If we rotate it around, you see that area between the 2 curves that I just shaded in, and I happen to draw in just 3 cross sections. Now, what do you know about all of these cross sections? They are all squares, right? So now what we're going to do, though, is we're going to build a shape where we just put in a ton of square cross sections. Think of tiles here. Like this is a 2-dimensional square, but maybe it's got a little bit of a thickness. And we're just going to stack them from one area of the region to the other area of the region. If we were to do that, we would get a solid. So let's go ahead and create that solid. So now, and I'll rotate this as well. What's the story with this solid? You can see it building on the backside. All right. I don't even know what you call that. Some maybe, futuristic building, possibly, I don't know, half of a weird shaped pill that you wouldn't want to take. I don't know. I have no idea. But it's a solid. We can all agree with that. And we should also all agree that if I draw in a cross section perpendicular to this case in the x-axis, right? Because all of these were drawn perpendicular to that red x-axis. Any cross section that I draw there is going to be a square. All right. So let's go ahead and stop the rotation. Let's do a little reset here. Whoop. and then just go back to showing 3 cross sections. So I want to find the volume of that. So how in God's name am I going to do it? All right. It seems a lot more razzle dazzle and difficult than it actually is. So here we go. Here's that region again. And you can see how I have this little line here. Okay. So what's that line all about? That line is representing the cross section, a representative cross section. Now notice if I'm going to draw this to be my base, then the square would be coming at you. It'd be coming out of the screen, right? And that's why when you saw me draw or do this picture here, right, you see how it's skewed? I kind of had to like skew the axes so you can see this square right here, right? You're not going to see that if I'm drawing this thing flat like this because it would be coming at you. And hopefully that makes sense. Notice also that the cross section is what? It's perpendicular to the x-axis. So that's going to be pretty important for you because if it's perpendicular to the x-axis, then take a wild guess what your eventual integral is going to be in terms of, right? It's going to be in terms of x, okay? So you notice that your cross section is going to be perpendicular, in this case, to x. And they don't always have to be, but in this case, they are. That's kind of how I'm structuring this, all right? That would be given to you. So, all right, so what do we need to do here? Well, the first thing we need to do is remember this curve y equals 4 minus x squared. It does that forever. We're not interested in that. Y equals x squared. It does that forever. So we want to stop here, and we want to start essentially here. So we have to get those values. So how do I find out when these two curves intersect? Method of substitution. Some of you say set them equal. That's going to work only because they're both y equals, but that's fine if that's what you want to do. And now solve this. So add the x squared over. Divide both sides by 2, and then plus or minus square root that left side, right? Square root principle, and then that's what you get. So this value here, whatever this x value is, it's like radical 2, and this x value here is going to be negative radical 2, which approximately is 1.414 and negative 1.414. And that's why I put that left bound and right bound in before on that GeoGebra app. All right, so you're like, all right, I got that. How the heck do I find the volume of this solid now? This is going to be a little bit bananas. And maybe before I do that, let's go ahead, say hi to Emma. Let's go ahead and that's not going to work. Let's try this. Whoop. Cross out there, a little control 1. All right, so that's not going to work. That's all right. So let's go ahead and scroll down here a little bit. And I drew just another shape for you, right? So there's the same region. Notice here's the skew of the axes. And that vertical strip that you saw here is now I'm able to actually draw it in as a square so that I can show that third dimension, all right? And this is another generation, I believe I did this in Mathematica, that created what the shape would look like. Sometimes it's kind of difficult to envision what these shapes would look like, right? So I want to figure out the volume of this thing here, this futuristic, I don't even know what it would be, building, whatever it is. How in God's name am I going to do that? It's actually really easy, all right? It is not difficult by any stretch of the imagination. So when we were doing volumes by revolution, what did I have you do? If you remember, I always had you start with the volume of a representative cross-section, right? So volume of a representative cross-section. So in other words, before it was just, what would the volume of just one washer be? Or what would the volume of just one disc be? Well, now it's going to be, what is the volume of just one cross-section? So now you look at this and you're like, it's a square. There's no volume there, right? The area of a square is s squared. How do I make this a volume? Well, just like we did with the circular discs and washers, we gave them thicknesses so that they can have a volume. Do the same thing here. Don't think of it as just a square. Think of it as like a square tile, all right? That's got volume to it. Okay, so I want to find the volume of that thing. So obviously it would be the area of the square, which is that face, times the thickness. Well, guess what? Your only choices for thickness in this class will either be delta y or delta x. And also, guess what? It's whatever your cross-section is perpendicular to. So this cross-section here is perpendicular to the x-axis, right? So it's going to be delta x. So if you're a good student, you would note just, maybe you write, hey, it's what you're perpendicular to, whatever you're perpendicular to. So now you're like, yeah, well, what the heck is S though, right? S is the side of that square. So S runs from this red curve down to that blue curve. So that distance is going to be S. And you're like, well, how do I find the distance between two curves? Well, it's just going to be the greater value minus the lesser value. It's going to be the greater y minus the lesser y. So it's going to be 4 minus x squared minus x squared. And that'll get you this distance right there. So that is your side. Squared delta x, and then this is volume. We'll just do RC for now on, right? Not RC Cola, not radio control, but representative cross section. Hopefully some of you know what RC Cola is. And that's it. And this represents the volume of just one representative square tile wherever I choose to draw that tile. Now, obviously, you can spruce this a little bit, so let's go ahead and spruce, right? Minus x squared, that's going to be minus 2x squared delta x. Now, this isn't necessary for you to go ahead and do this when you're doing these problems, but I like to do it because it contributes to the understanding. So again, remember what I would say when we did discs and washers. I would say, hey, what's the deal? Do I care about the volume if there's just one representative cross section? And the answer would always be no. So what do I want to do? I want to add up all of these cross sections as their thicknesses go to 0. What is that the process of? That is the process of integration. All right, so let's rock and roll. So volume equals, these are the things I'm adding up. So it's going to be integral, right? There's no pi here. This is no circular disk, right? It's going to be the integral of 4 minus 2x squared dx, right? That's it. That's you adding up all the square tiles as the thicknesses go to 0. Well, where do I start? You start at this x value that we found before, minus radical 2. Where do I end? At that x value, positive radical 2. Everyone's in terms of x, blam, that's going to get you the volume of this guy right here. Now, if you were doing this by hand, it's not that it's impossible. Might be a little bit annoying. What are things that you can help yourself out with? You'll notice both these functions are even, aka they're symmetric to the y-axis. What does that allow you to do? You can leverage symmetry here, and instead of going from, and I'll write it out, instead of going from negative radical 2 to radical 2, you can go from 0 to radical 2. And you're like, well, what's that going to do? That's going to only get you half the volume if I go from 0 to radical 2. And you'd be correct. So what do you need to do? You need to double it, right? So again, if you're doing it by hand, that's great because now you're plugging a 0 in as opposed to a negative radical 2. And who wants to do that? Answer is no one. All right, so now what do you do with this, right? If you want to integrate this, and I'm not going to do this by hand with you because it's just, it's going to take a little bit of work and time here on this, and it's not necessary. But I will talk about how you do it, and you should probably do it to see if you have that ability. All right, you cannot, I repeat, you cannot view this as stuff squared, and they're like, oh, it's just going to be 1/3 stuff times 1 over the derivative of stuff, right? That's like that U substitution you taught us in our head, that reverse chain rule that doesn't really exist. You can't do that. And do you know why you can't do that? So take a second, maybe hit pause and think about that. Why can't I do that? All right, so you're back. So you can't do it because your U would not be linear. If you were to rip through a U substitution here, let U equal 4 minus 2x squared, your du would have an x dx in it, right? And there's no x out here. So this cannot be done with a linear U substitution, okay? Can't be done with a U substitution. So like, all right, so what am I going to do then? Well, lucky for you, it's only squared. Even though that doesn't look like a 2, that looks like a seagull flying around, that is a 2, all right? So in order for you to do this, what are you going to do? You're going to multiply it out. That is correct, right? So FOIL this out, distribute it out, however you want to think about it, because now you'll have the integral of the sum and difference, which of course is just the sum and difference integrals, and then knock yourself out. Go get them, all right? I don't want to do it that way. I'm going to do it with a calculator because you need to know how to do integrals in your calculator, right? So how would we do that? Well, think about it. In our calculator right now, and you never write calc syntax on your work, by the way, but I'm doing this for just note flavor, right? In Y1 right now, we have 4 minus x squared. And in Y2, we have y equals x squared. So I'm integrating, if you think about it, before I simplify this, y1 minus y2. So this expression here is y1 minus y2 and then quantity squared. So if I go ahead now and go over to my little app here, right, I can do math 9, right? I'm going to go from, the calc, who cares if the calc has to do work, right? So I'll go from negative radical 2, bear with me here, positive radical 2. And then we're going to go now vars, y vars, function y1 minus vars, y vars, function y2. And then you can't forget now, which this is going to be a little bit annoying the way this calc's doing it for me. I have to do all of this squared. All right. So right now my parentheses are not kosher. So hopefully it lets me insert right here. So if I go second, insert, and then put a parenthesis in, that didn't work. Oh, that's just lovely. All right. So let's try that again. So let's go parenthesis, vars, y vars, function y1 minus vars, y vars, function y2, and then close the parenthesis, squared, and then with respect to x, that took way too long. All right, but you get the idea, and then you hit enter, and then there you go, 24.1359 ... All right, so it took me a little bit to do that on the computer. I was working with the tablet, the microphone, and the keyboard at the same time. You'd laugh if you saw what I just did. All right, so anyway, so that's that. So 24.1359 ... We'll go accurate to 4 decimal places. So let me go back here. Let me go back here. And let me write what I had, which is 24.1359 ... Okay. And there you go. And that's the volume of this funky looking thing right there. And if you think about it, the algorithm for solving this is basically identical to the one with the revolution, right? You start with the volume of a representative cross section, and then you understand that integration is the process of adding things up as a certain quantity goes to zero. That ends up getting you the volume. All right, so that's a pretty cool question if you ask me. All right, so let's rock and roll. Let's move on here. Let's do the next question. So now the cross sections aren't always squares, right? So should you panic? So we got semicircles here. You have equilateral triangles. Sometimes you have right isosceles triangles. I'm going to jump to the right isosceles triangle question. I get that this video is going to be longer than normal, but remember, this is optional for you. So I don't really mind. Okay. All right. So here we go. So let's do this. Let's make now a solid where all of the cross sections are right isosceles triangles. And we're going to do it in a way where the leg is in the XY plane. Because technically, if I wanted to, I can make a right isosceles triangle, put the hypotenuse there. So you have to pay attention to stuff like that. So the leg is going to be in the XY plane. So now before we get going, again, just so you can somewhat visualize this app is pretty neat in that, all right, what if I had a triangular cross section, right? So now we're talking about the same region, the same area is the base of my solid, right? But now our cross sections are triangular, and maybe I'm going to show 3 in now, all right? But again, we don't just want 3 cross sections. We want a bunch from left to right that are going to basically create this shape. And also remember that we want these cross sections really to have thicknesses, so they'd be like triangular plates and not just these 2-dimensional triangle looking things that you see there. If I create the solid, hopefully this doesn't bring everything to a crashing halt. Sometimes it does. You can kind of sort of see what the shape would be. All right, so that's kind of tough to see. Maybe if I shut these off and you create the solid this way. All right, so it's not the best graphic. I guess it's really trying to, show you 3 dimensions and 2 dimensions. Let's rotate again. All right, that's not the best. I've seen better. I think the picture that I have generated might look a little bit better than that. All right, so let's go ahead and pause that. Let's go back to here. And did I not generate it? I didn't generate it for that one. So it'd be a little bit different. It'd look kind of like, the shape would look different. I don't even know what you'd call it. It almost would look like, quite honestly, like the I think it's called the bill of a duck, right? The beak, whatever that thing is. It would kind of look like a 3-dimensional one of those, which would be pretty neat. All right. So anyway, whether you can visualize it or not, quite honestly, doesn't really matter because you're going to be asked to find the volume of the solid that's created there. Okay, so the volume of, in this case, the beak. So how are we going to do that? Well, again, not so difficult. All right, how do you start? You start with the volume of a representative cross section. Well, what's my cross section now? My cross section is a triangle, right? This guy here, where this is like the base, there's the right angle, and there is the height. So now I could do 1/2 base times height for the area of this triangle. And to give it a thickness, it'd be kind of tough to draw maybe with this perspective. Who the heck knows? To give it a thickness, you kind of, I guess, wouldn't see it the way I drew this. This thickness would be back here. You would just do delta something. And what is a delta? It's always delta what you're perpendicular to, right? I can say have your cross sections be perpendicular to the y, and you would do delta x there, or delta y there. Okay, so that's that. So you're like, all right, so what's the story with that? You know, base and height, that's a little bit problematic because there's two variables there, so maybe you're upset about that. But here's the deal. This is a special triangle. This is an isosceles right triangle. So whatever this base is, guess what? It's the same as that height. So you really want to leverage that. In fact, I probably would have went straight to 1/2 and whatever you want to call it, leg squared, base squared, whatever it is. That's going to be the volume of your representative cross section. Now, what is your base? Your base is the distance running from this curve to this curve. So as you know, to get vertical distances in the XY plane, it's just top minus bottom. If you needed a horizontal distance, if you're doing things with respect to Y, guess what it would be? It'd be right minus left, more positive minus less positive. So the volume of my representative cross section here would be 1/2. So what's the base? It's the top, 4 minus x squared, minus the bottom, which is x squared, right? So that's 1/2 base and then squared delta x. You're like, holy cow, that looks a lot like the square one we just did, just a little bit different. In fact, there's a half there. So now what's the story? We don't want the volume of just one of these representative triangular discs, right? We want to add up all of the triangular discs as the thicknesses go to 0. What is that the process of? It's the process of integration. So volume equals integral. What am I integrating, right? I'm going to integrate this here. This was the volume of representative disk. So I'm going to pull the half out because we know we can pull constants out. And then I'm going to do 4 minus x squared, right? 4 minus x squared. That's like my y1 right now, my calc, minus x squared. And then dx, right? When you put the integral in, you put the dx. Don't put the delta. And you're going to go from negative radical 2 to radical 2, all right? And then don't forget the squared there, right? And that will get you the volume of that duck beak or whatever it might be. Again, if you're doing this in a calculator, you literally just leave that. You don't try to be a hero, and you go straight to what your answer would be. And if you think about it, let's go back to our calc here, okay? If you think about this, I mean, we basically just did this, right? So we integrated from negative radical 2 to radical 2 of top y1 minus bottom quantity squared right here. So all I have to do is multiply that answer by a half. So if I do that without redoing all the work, because I want to somewhat be efficient, times 0.5, all right, there you go, 12.0679. All right, so that's what I'm going to come up with. So 12.0679. All right, so I'm going to write that down, all right, right here. Let's go to my pen, 12.0679 ... cubic units, okay? Now, I should talk about, well, what if you had to do it by hand? If you had to do it by hand, you do the things that we talked about before, which is the same base here. So it's still symmetric to the y-axis. So that means I'm going to do half of the volume and then just multiply it by 2, which would be good news because then those would cancel. And then this would just be 4 minus 2x squared. Again, you can't do a u sub here. You'd have to multiply this out and then do integral of sum integrals, which not impossible, but definitely takes some time. Okay, so that's how you find the volume of solids with known cross sections, where we use some area in the xy plane to be the base. Now, I did these with respect to x. All I had to do is say, hey, let's make the cross section perpendicular to the y-axis as opposed to the x-axis, and then everything would be done in with respect to y, much the same way that you did the revolution problems with respect to y. Okay, so I only went over 2 problems. I get it. That's not a ton. I'm going to stop here because the video is longer than normal. But again, this was just for you. So if you want to go ahead and attack just for fun, some of the other problems that I had on here. So one of them was, let's see, now we'll have equilateral triangles, and that one I actually drew. That would look very similar to the duck beak I was just talking about. The cross sections are equilateral triangles. That's gonna, you're gonna have to think outside the box to get this guy. When you go to do volume of the representative cross section, you're gonna need to think a little bit. But I'll let you attack that if you want to. And then we have semicircles. So that one should be pretty easy. That's very similar in fashion to the 2 that I just showed you. So if you want to attack those, I can't promise I'll give you extra credit. That's up to you. And then there's this guy too, squares with diagonals in the XY plane. So now we're lining up, we're basically like sliding the square in, so its diagonal is in the XY plane. So that's kind of crazy because that wouldn't have a flat base. Those are 3 extra problems. If you want to do them, great. You can submit them to me, and I'll check them and I'll give feedback. And if people actually do it, then I'll come back on here and I'll work these 3 problems out. If you don't, that's fine as well. I'm not saying you have to do it. I'm just kind of enriching, you. This was in the curriculum. This really was the only unit in the curriculum that I have not shown you. So now I've shown it to you. But remember, it will not be on this year's AP exam, all right, which is 2020. But in the future, it will be back on, I'm sure. So that's that. Hope all you guys are well. Hope you're safe. Hope you're not stressing out. Take everything in stride. Maybe do a little breathing every day, a little yoga every day. It's great for the mind. Be good. Again, if you have questions, text me. I'll get back to you almost immediately. Yeah. All right. So be good. Take care.